Hi everyone, in this video I am going to show you solving or evaluating limit of a function, an overview of doing that. So the question is, how do we find the limit of a function given a graph, given table of values, or given an algebraic expression? So under algebraic expression, you can see there are six things there I need to discuss, and I'm going to give at least one example for each. Okay, let's start with the graph. So here we have this piecewise function. This includes a one-sided limit. So what's the limit of this function as x approaches 4 from the right side? So this is your 4. So from the left, this is our graph, and it's going to approach this point here. It's undefined at this point, but it's approaching that point, which is equal to 5, right? Now, what about the limit of this function as x approaches 4 from the right side? So that's all the x's here. And then looking at the graph, it's approaching this point. It's defined at this point. F of 4 is defined at the right side of this graph, and the answer is equal to 3. Right? Now, this is a very general question. What's the limit of this function as x approaches 4? So if that's the question, you have to solve both the um, limit, the left hand limit, and the right hand limit. And then you need to compare the two. So here, since 5 is not equal to 3, the limit does not exist. They should be equal for the limit of this function to exist. All right, let me give you another example. Again, here we have a piecewise function, but let's check if there's a limit of f of x as x approaches negative 3. So again, if the question is like that, you have to solve the left hand limit and the right hand limit. So the left hand limit, this is our negative 3. Left hand limit is approaching this, that's 1. And then the right hand limit is this side of the graph, and it's approaching negative 2. So since the left hand limit, which is 1, is not equal to the right hand limit, which is negative 2, the limit of this function as x approaches negative 3 does not exist. Now let's check the limit of this function as x approaches 2. Again, we need to look at the left hand limit. So looking at this graph, it's approaching this point. Okay, so it's not defined at this point for 2. Okay, as you can see, that's an open circle, but it's approaching that part of the graph, which is 3. So the left hand limit is 3. The right hand limit, okay, so what is the limit of this function as x approaches 2 from the right side? So we need to look at this point. There you go. As you can see, it's approaching the same point, which is also 3. Although f of 3 is equal to 6, all right? Or f of 2 rather, f of 2 equals 6. It's not approaching that point. It's approaching this point 3. So they are equal. The limit of this piecewise function as x approaches 2 is going to be equal to 3. All right? Now let's consider the last graph. What is the limit of this function as x approaches negative 1? Again, if it's a graph, you need to look at the left hand limit and the right hand limit. Okay? So let's look at the left hand limit is going this way as x is approaching negative 1. So as you can see, it's approaching up there, which actually tells us that it's approaching positive infinity, right? It's going to be infinitely bigger, the value of this, I believe, rational function. So, and then if you look at the right hand limit, it's going down here, which is approaching, in terms of y, approaching negative infinity. So they are going in a different direction, obviously, which tells us that the limit of this function does not exist. All right. So that is in terms of graph. What about if you are given table of values? So here we need to find the reasonable estimate of the limit of this function as x approaches negative 5. So the negative 5 is obviously right here in the middle. All right. So these are the values of x, the blue one, the values of red. Those are the y values, f of x, the output. So the y values from the right side or left side rather is approaching, what do you think? That's negative 1.998. I believe it's approaching negative 2 from the left side. Now if you look at the right side, the values are approaching negative 2 as well. Now notice that they are equal. So meaning the answer of this one is negative 2. Right? So the left hand limit and the right hand limit should be equal. Let's try another example given table of values. Here we need to find the reasonable estimate of this function as x approaches positive 2. So I'll draw that vertical line in the middle. That's your positive 2. Look at the left hand limit. Oh, it's getting bigger. Look at that, negative 3,999. And it's negative, right? So I don't know, maybe it's approaching negative infinity. And then on the right side, from 941, 401, 4001, it's really becoming a big number, and it's not approaching a certain number, it's approaching positive infinity, and they are not equal. If you see that kind of pattern, the limit does not exist. They're not equal. Okay? All right. Let's have another example, and I think this is the last one. So what is the reasonable estimate for the limit of this function as x approaches 4? And 4 is actually here in the middle. It's defined. Okay? And maybe you're thinking, since f of c or f of 4 equals 5.35, then that's the answer. Well, let's examine the values. Okay, let's examine the values. So here, as you can see from the left hand limit, 3.47, 3.58, and then it becomes 3.67, and it stops at that point. Now you look at the jump, okay? You look at the x and the corresponding y value. So at 3.999, I mean 3.99, the result or the output is 3.67. And then it becomes, if you input 4, it becomes 5.35. So if you imagine this graphically speaking, this is like almost the same. And you look at the right hand limit, it's getting closer and closer to a certain point, but 4.00, and then when you put the 4, the answer is exactly 4.35. Now this reminds me of the graph that we had earlier. Let's look at that graph. This one, right? It's approaching a certain point. Obviously, if you put 1.999 here, the answer will not be 3, but it's going to be close to 3. Similarly, if it's 2.001, it's going to be closer and closer to 3, but it's not going to reach 3. It will be undefined at 3, in fact. But if you plug in that 2, you evaluate 2, the answer will be 6. So, which tells us that if we look at that table, this one, and they are equal, look at that, 3.67, 3.67. So that means it's telling me that the reasonable estimate for the limit of this function as x approaches 4 will be 3.67. Right? The limit of a function is not always an integer, so there's a possibility that it can be nezable like this one, especially if you are observing table of values. Right? So I think that's the last one for the table of values. Now, what if it's an algebraic expression? I have six topics here under that. Let's consider the polynomial function. So here, when we say polynomial, it can be quadratic, cubic, linear, a constant function. Uh, it can also be, I believe, this is not under polynomial function, but we can also relate this to some functions such as exponential or logarithmic, as long as it's not in fraction form. So what you're going to do is simply substitute that negative 3 to x. So here, let's say negative 3 squared plus 4 times negative 3 minus 9. So negative 3 squared plus 4 times negative 3 minus 9. Negative 3 squared is 9. This is minus 12 and then minus 9. So you have a 9 minus 9 which is equal to 0. The answer will be negative 12. So that's for a polynomial function. What about a piecewise function? So for the piecewise function here, you can see there's only one question. It's not like you need to find the limit from the left or from the right side, but you need to do that in a piecewise function. Um, in reality, you can actually do this, like to find the left hand limit and the right hand limit for a polynomial function, but it's not nearly necessary for that kind of function. But for a piecewise function, you need to do the left hand limit and the right hand limit. So let's do the left hand limit, which means we need to look at the less than symbol, provided that the x is here on the left side. We will use this 2x plus 7. So that's 2 times 5 plus 7, which is equal to 17. 2 times 5 is 10 plus 7 is 17. Now let's look at the right hand limit. So that means we need to look at the greater than symbol, provided that the x is on the left side. So this is 5 squared minus 10. 5 squared is 25 minus 10 is equal to 15. And again, here we have a situation wherein the left hand limit is not equal to the right hand limit. Therefore, the limit of this piecewise function does not exist, right? So that's for the piecewise function. Let's go to the rational function. So in a rational function, you can actually first directly substitute that 3. But if we do that mentally, let's say here, 3 squared is 9, negative 2 times 3 is negative 6. You add negative 6 and negative 3, that's negative 9. 9 minus 9 will be equal to 0. So if you do the direct substitution, this will be undefined. So if that happens, what you can do next is try to simplify this. And how? We need to find the factors of both the numerator and the denominator. So in the numerator, we have a negative 24. That means the two numbers we're looking here should have different signs. Let's take, for example, 8 and 3. Now, since the middle number is positive, the higher number should be positive. Okay, so that's x plus 8, x minus 3. 8 times negative 3 is negative 24. Positive 8 plus negative 3 is positive 5. Now, in the denominator, we only have 3 as a constant number, so that's easy. It's just 3 and 1. The higher number should be negative because the middle number is negative here. It's negative 2. This one. Negative 1 times, negative 3 times 1 is negative 3. Negative 3 plus 1 is positive 2. Now, here you can clearly see that we can cancel out x minus 3, which tells us that this is just x plus 8 over x plus 1. And now we can substitute that 3. So 3 plus 8 over 3 plus 1, which is equal to 11 over 4. Righty? Let's go to the next one. That's for the rational function. What about functions with radical? So here, in the numerator, we have the radical sign, and that's the part of the um, function that you have to focus on. So that means here we need to multiply both the numerator and the denominator by the complex conjugate of the numerator. So complex conjugate of that is square root of x plus 12 plus 4, right? So if we multiply the numerator, we simply multiply the first terms and then the last terms. So square root of x plus 12 times that will be equal to x plus 12. And then negative 4 times positive 4 is negative 16. In the denominator, what I will do here is I can see that this is going to be x plus 12 minus 16. This is minus 16, by the way. That's going to be x minus 4. And I can see that in this negative 3x plus 12, I can factorize this and come up with a factor that is x minus 4. So to do that, what I will do is I'll take out that negative 3, and this will be x minus 4. Look at that. And then I would just copy this, square root of x plus 12 plus 4. Right, now I don't need to do that. I'll just rewrite that over again. So let me just do this. This will be equal to x minus 4. Okay, so now I can cancel that x minus 4. Okay, so that leaves me 1 over negative 3 square root of x is 4. So this is 4 plus 12 plus 4. 4 plus 12 is 16. Square root of 16 is 4. So 4 plus 4 is 8. So 1 over negative 3 times 8. So the final answer is negative 1 over 24. Alright, so that's for function with radical. What about complex fractions? So let's check this one. Okay, so here the denominator or the entire thing is actually in a complex fraction form. So in order for us to simplify this, what I will do first is I notice that negative 2x plus 10 can be simplified. So I will factorize rather. So I'll factorize that. Negative 2, then x, and then I think minus 5. Now in the denominator, we will do that butterfly method because the denominators are different. The denominator, multiply them, x plus 4 times 3. And then we cross multiply. 3 times 3 is 9, minus. I'll put the 1 here, and then x plus 4. And then this will be equal to the entire numerator, which is negative 2 times x minus 5, times the reciprocal of what we have in the denominator. So negative 2 times x minus 5 times x plus 4 times 3 all over 9 minus x minus 4. Now I notice that I can combine 9 minus 4, that gives me 5. So this is negative x plus 5. Now look at this. Oh, I can't cancel this one. We need to change the signs of the one that we have here on top. So let's make the 2 positive. Let's make the x negative. And then let's make the 5 positive. And look at that. They're now the same, which means we can cancel them. And that's going to give us positive 2 times x plus 4. So that's 5 plus 4 times 3. So 5 plus 4 is 9. Times 3 is 27. Times 2 is 54. Right, so 54 is the answer in this problem. Let's go to the, I think, last one, I believe. What if it's a trigonometric function? So for this kind of problem, you need to at least understand some of the identities, and you need to be familiar yourself with simplifying expression, obviously. So here I can see that 3 and negative 3 cosine square x can be factorized. So what I will do is I'm going to do that. So 3 times 1 minus cosine square x all over 4x square. Right? So we understand that 1 minus cosine square is just sine square x, right? So that means this is equal to the limit as x approaches 0, 3 sine square x all over 4 x square. Now once you reach this point, you are going to apply some of the properties of limits. So meaning we can actually take this out, this 3 over 4, like we can write this as 3 over 4 times the limit of sine square x over x square as x approaches 0. Now you might be thinking, oh, now I can substitute the 0. Now hold on, we can still do something about this problem. So what I'm going to do is I'm going to factorize the sine square x and the x square. So the reason why I will do that is because I'm going to show you something later on. So this is limit of sine x over x. My bad, my bad, my bad, my bad. Limit of sine x over x as x approaches 0 times limit of this function as x approaches 0. So we can do that. All right. So now you need to know this. Limit of sine x over x as x approaches 0 is very special. You might be thinking that the answer there is going to be undefined. So there are two ways of actually solving the limit of that one. The first one is using table of values. So meaning you will substitute all the numbers from the left side that is less than 0, and then all the numbers from the right side that is greater than 0. So from the left and from the right side, and you will see that it's going to approach a certain number, and it's not 0. Okay, the answer will be 1. So this is 1, and this is also 1. So meaning this is just 3/4 times 1 times 1, and the final answer is 3 over 4. And you might be wondering, prove to us that the limit of sine x over x as x approaches 0 is equal to 1. Table of values, that's a lot of work. I will show you the graphical representation of that function. So if you graph sine x over x, you will see this function. And it's obvious that as x approaches 0 from the left, and as x approaches 0 from the right side, it's going to reach this point, which is equal to 1. This is just, I think, one of the few special trigonometric function that you will see. All right. Okay, so I think that's it for today. I hope I was able to give you a more understanding on how to find the limit of a function. All right, so if you like this video, please share this video to your friends so that they will also understand the summary and the overview on how to find the limit of a function. All right. Again, thank you for watching and have a good one. Bye.